Okay, I hope the PPT is visible. Okay, so in the last class we were discussing about the 3D reconstruction of cameras and structures. That is, how do we go about 3D reconstruction, right? And we just began with some of the just the basic steps of the reconstruction and about some ambiguities. That is, with respect to what would be the kind of transformation that or what would be the kind of space that we would be in. That is, whether it's Euclidean or similarity when we go about with reconstruction. So we just go through the introduction of the 3D reconstruction just quickly, where we stopped last class, and then we'll continue with today's class with more details on the 3D reconstruction. Okay, so what we saw last class were what are the different basic steps in the reconstruction method. That is, let us say that the camera parameters, okay, it is not known to us. If it is not known to us, then how we can go about with the reconstruction would be first to compute the fundamental metrics from the point correspondences. So if you remember the epipolar geometry diagram, we saw that there would be two image point pairs or correspondence pairs that we can identify. That is, given two images of the same 3D scene, we can identify correspondence point pairs. That means those points which are present in both the images. So let's say you have an image over here. Let's say this is image 1, and let's say we have another image here which is image 2. Okay, both of the same size, and let's say you have a 3D point over here, okay, which is represented by, say, capital X. Now the image of this particular 3D point may be somewhere present over here in the first image. It may be somewhere present, let's say, here on the second image. Okay, so in that case, let's say this is determined by the point X and this is X dash. Okay, and basically these 2 points, that is X and X dash, which are the image points. These two image points actually, both of them, they correspond to or they indicate the same 3D point, or they are images of the same 3D point in the scene, right? So therefore we can call the points X and X dash as image correspondence pairs. So from these image correspondence pairs, we can first calculate the fundamental matrix F. Okay, and from F we can then calculate the camera parameters. So let's say the camera parameters are given by PP dash, right? And from this we can also calculate, from the image point pairs we can also calculate what is capital X. Okay, so the different steps would be given the image point pairs. So let's say the image point pairs have been calculated by some methods. Let's say, for example, by matching using correlation metrics or so on. After we have identified the correspondence pairs, we can calculate the fundamental metrics, and from the fundamental metrics we can calculate the camera parameters as well as the 3D point X. Okay, and these camera parameters P and P dash, it is inclusive of, or it contains both the internal as well as external parameters. Okay. Now, this is a case when we have the uncalibrated camera parameters. That means that is what we are assuming is that the camera parameters are not known to us. In that case, we call it as an uncalibrated camera, and in that case, we can compute the fundamental metrics. If the camera is calibrated, right, that means if the internal camera parameters are known to us, then instead of fundamental metrics, what we do is we compute the essential metrics. Okay, but the remaining steps would remain the same. So these are the basic 3 steps. We were discussing about this in detail, right? In the previous class about how we can compute the fundamental metrics, the camera matrices P and P dash, and how we can finally calculate the 3D point X. Okay, that is using triangulation method. Triangulation method basically means that you use the epipolar constraint over here. Okay, that means if we know here we know what is the parameter or the camera C. You have the camera C dash, okay, and corresponding to camera C, I have the parameter camera parameter capital P, and corresponding to C dash camera C dash, I have the parameter P dash capital P dash. Okay, so given this, what I can do is using the camera pinhole camera projection model and given the image of the point X, I can just project it, okay, to get this particular line. So I get this particular, okay, it's this line, okay, it should come like this. Okay, so I have this particular line here, and I know that the actual 3D point lies somewhere along this line. So to identify where exactly it lies, what I do is I need the help of a second image or a second image point pair, correspondence pair, and from this I again use the pinhole camera projection model to project it, and after projecting it, the point of intersection of these two lines would give me the 3D point. Okay, so these were some of the points that we have discussed, and this method, which is known as a triangulation, it works well for all the 3D points which are lying along this epipolar plane, right? Now, you find that this triangulation method, it does not work if the image that you have is lying on the baseline. So baseline is basically the line which is connecting the camera, centers C and C dash. So this particular line is called the baseline, right? So if we are considering the images, that is, if this X is lying over here, now you know that this point, it is called as the epipolar point E, and this is the epipolar point E dash, right? So if the epipolar point itself is the image correspondence pair that we are considering, then this triangulation doesn't work, because what we are trying to do is we'll be trying to project the line which is joining this particular camera center with that of the image, and we are saying that in this projection you'll have the point, right, the actual 3D point, but the corresponding image point pair is this one, and again it lies along the same line. That means here the point of intersection is basically the whole, all the points along the line would intersect, right? So at this particular stage, if the image pairs that we are considering is basically the epipolar points itself, then what we say is this triangulation method doesn't work. Okay, so just note that. Okay, and then in last class we discussed about the reconstruction ambiguity. That is, once we have reconstructed a particular scene, okay, given two images, there are some ambiguities which may be involved. So one ambiguity is with respect to the placement of the scene, okay, that is, we do not know how exactly it is placed with respect to the 3D coordinate frame. That is, if I try to take the world coordinate frame, once we have reconstructed a particular scene, okay, just from the image point pairs alone, we cannot say where exactly that reconstructed scene is with respect to the 3D world coordinate. What that means is we do not know where exactly in this along the longitude or latitude, what exactly is the values, or where exactly it is positioned in this world, okay, or with respect to the directions. Is it if it is a particular lane or a street, okay, along which direction does it actually move? Is it north or south or west or east or so on? So such information we cannot derive from just the image point pairs alone. We will need some kind of extra information, right? So that kind of ambiguity with respect to the position of the reconstructed scene is called as a reconstruction ambiguity, and this is with respect to the placement of the scene, right? And in such a case, what we can say is that the scene is determined at best up to the Euclidean transformation with respect to the world frame. That means what we have reconstructed, the scene which we have reconstructed, would be a Euclidean transformation of the actual scene, okay? So the actual scene, wherever it is, right, or with respect to the world coordinate whatever be the values, if you just transform that with respect to rotation and translation, we would get the reconstructed scene, or what we have reconstructed. If we apply a Euclidean transformation, we will get the actual values with respect to the world frame. Okay, so the kind of transformation that exists between the reconstructed scene and the actual scene is Euclidean transformation, if you are considering the reconstruction ambiguity with respect to placement alone. Okay, but you also see that it is not just placement, but you also may have a ambiguity with respect to the scale of the structures which are present inside the reconstructed scene. That is, for example, if we have reconstructed a particular scene with only using the image point parameters or the image point correspondence pairs, what we see is we have reconstructed the structures, but what exactly is the length, okay, or what exactly are the is the angle between each of these lines, okay, or what exactly is the length in terms of, let's say, meters or centimeters or so on. So this kind of information would not be present, okay, if we just consider the image point pairs. So we will need some extra information with regard to the length of the objects, okay, or a particular scale would be required in order to know what is the actual measurement, right? So that kind of ambiguity is called as scale. Okay, so basically what we are trying to say is, using just the image point pairs, okay, just x and x dash alone would not be sufficient to know what is the scale of the reconstructed objects, and we will need some extra information with regard to that. Okay, some information which is obtained apart from the image point pairs. So in such a case, when you have an ambiguity with respect to the scale, what we can say is that the reconstructed scene is up to a similarity transformation. What that means is the reconstructed scene would be or on applying similarity transformation on the reconstructed scene, we can get the actual scene. Okay, so similarity transformation means along with the previous rotation and translation, we are also adding an ambiguity with respect to scaling. Okay, also a transformation with respect to scaling would also be required if in case the scale information is not available. So what we are trying to say here is that if we are depending only on the image point pairs or the information with regard to the correspondence point pairs, there would be some ambiguity with respect to the position as well as scale of the reconstructed scene with respect to the 3D world coordinates or the 3D world frame, right? And that kind of ambiguity is what you can generally call as a reconstruction ambiguity. And mathematically you can represent it this way, that is, let us say that xi be a set of points and p dash are the camera parameters, okay, the two camera parameters, and let's say the image point pairs that you have is small xi and xi dash, right? So what we said earlier was that if we are having a reconstruction ambiguity, right, with respect to the rotation, translation, and scaling factor, okay, that means it is the similarity transformation, right? So we can represent that transformation this way, that is, I can write hs is equal to r t 0 and lambda, where r represents the rotation matrix, t represents the translation, and lambda is a scalar quantity which represents the scale, right? So here what I can say is, the if I can just write it as x dash is equal to hsx, that means hs, which is for the similarity transformation, and x for the reconstructed point. Okay, so that means if I or I can put it as x cap also over here. So what that means is, to the points which I have obtained, the reconstructed points, okay, to those reconstructed points, if I apply the similarity transformation, I can get the actual 3D scene or point pairs or the points which are present in the actual scene. Okay, so that means the actual scene as well as the reconstructed scene would be differing only by a similarity transformation, or it will be related by a similarity transformation. If I apply a similarity transformation to this reconstructed scene, I will get back the actual original scene. Okay, so that's what it means. Now, another point that you need to remember is that if we are applying the similarity transformation to this point xi, okay, so that when I apply the similarity transformation, what I get would be hs xi, right? And if I again apply the similarity transformation to the camera parameters p and p dash, when I'm applying to the camera parameters, it would be p h s inverse and p dash h s inverse, right? So on applying similarity transformation to the points as well as the camera parameters, what happens is it will not change the actual points which are present. Okay, so that means I know that x is equal to, I can write small x, okay, which is basically the image points, right? That is equal to the camera parameters capital P into x, which is the basically the 3D point, right? So on applying this, on applying the similarity transformation to this, okay, I can write it this way. That is, I get pxi is equal to phs inverse hsxi, right? So here this hsxi basically is the transformed image point, right? And here this phs inverse is basically applying the transformation on the camera parameters. Okay, so on applying the transformation on the camera parameters as well as on the reconstructed points, what happens is that here these two, this becomes an identity matrix, and basically it becomes pxi itself. So what that means is, as a physical interpretation, what that means is even after applying a similarity transformation, when I get a reconstructed scene, right, the image of those reconstructed scenes will remain the same. Okay, so that means whichever is the actual scene, right, and the reconstructed scene which I got, right, the image of these two, the image points of these two will still remain the same. If I represent it by x or x dash, that will remain the same. Okay, so this is one point you need to remember with respect to reconstruction ambiguity. That means it is related. The reconstructed scene may not be exactly the actual scene, right? So the reconstructed scene, which we have reconstructed from image point pairs, would be related with the actual scene with respect to some similarity transformation, right? And on applying the similarity transformation, we can get back to the actual world scene, right? And in order to know what is the position as well as the scale, we would need extra information, okay, apart from that of the image measurements. Okay, now here, so let's say this P, that is the image, the camera parameter P, okay. Let us say I'm decomposing that in terms of the internal parameter, which is given by capital K, and the external parameters, which is given by rotation and translation, right? So if I'm decomposing, or if I can represent the camera parameter this way, right? So if I'm applying the similarity transformation, I can write it as PHS inverse is equal to K RP R inverse T dash is what I get, where HS is equal to RT0 and lambda. That means on applying the similarity transformation on the camera parameters, what happens is the internal parameter does not change. Okay, it still remains K. The only change that happens is the rotation matrix changes as well as the translation matrix also, or the vector also changes. Okay, but the internal parameter does not change. Okay, so again, that is a point that you need to remember. That is, on applying the similarity transformation to this camera parameters, what happens is that the internal parameters of the camera does not change. It will only change the external parameters of the camera. Okay, so that means it is like as if you are changing the position of the camera, okay, but not exactly the internal focal length or any, let's say the number of pixels along the rows and columns of the pixel dimensions, all these are not changing. Okay, but what happens is only the external position of the camera would change when you're applying the similarity transformation. Okay, because basically the similarity transformation has only rotation, translation, and scaling involved in that. Okay, so therefore, multiplying by H's inverse, it does not change the calibration metrics of P, in the sense it does not change the internal parameters of P. Okay, and what you can say is that for calibrated cameras, the reconstruction is possible up to similarity transformation. That means for calibrated cameras means if the internal camera parameters are known, okay, internal camera parameters are K. If that is known, we can call it as the calibrated camera, right? So in such cases where the internal camera parameters are known to us, and that is what we are dealing with is calibrated camera, then the reconstruction would be possible up to a similarity transformation. That is, the reconstruction will happen in the similarity space. Okay, but what happens is, or what we can see is that for the uncalibrated cameras where the internal and external parameters are not known to us, then the reconstruction is possible up to projective transformation. Okay, so we'll be seeing that later, that it would be possible up to the projective transformation. What that means is the internal parameters would also change accordingly. Okay, so as long as calibrated camera parameters is concerned, you see that the reconstruction is possible only up to similarity transformation. That means simply keeping the internal camera parameters fixed. Okay, keeping this fixed, what happens is only by changing the position of the cameras you attain the similarity transformation, or the similarity transformation would imply that you are only changing the position of the camera parameters. Okay, now coming to projective ambiguity. As we have said earlier, that if the calibration of the camera is not known to us, okay, that means if we do not know the internal or external parameters of the camera, that means it's an uncalibrated camera, then what happens is the transformation that we'll be dealing with is a projective transformation. Okay, or the transformation that we would be representing would be up to, or what is possible, the reconstruction which would be possible would be up to a projective transformation. Okay, and this can be called as the projective ambiguity here, right? So if H is any projective transformation metrics that you have, right, then what happens is, so when we are trying to apply the projective transformation on the points, we can represent it as HXI, and when we are applying it on the camera parameters or camera matrices P and P dash, that becomes PH inverse and P dash H inverse, right? And on applying the projective transformation on the points as well as the camera parameters, what we will see is that it does not change the image points. The image points will still remain the same. So if that happens, then what we can say is that what we have been dealing with is the projective transformation, or the reconstruction which has taken place is basically a projective transformation. Okay, now there are some terminologies that you need to remember here. Okay, so let's say the image point correspondences that we're dealing with, the image point pairs are xi and xi dash, right? So for the true reconstruction, we can represent it by using a bar here, that is x bar, capital X bar I for the actual points. The actual camera parameters would be capital P here, capital P dash bar, okay, with the bar here, okay, which represents that it's the true reconstruction. That is the true reconstruction that we are looking for. That is the actual scene, 3D scene, okay. But when we are trying to reconstruct it, what happens is we may not get the true reconstruction, okay, but we may get some reconstruction which is related by a transformation, okay, and this transformation may be a similarity transformation if it is a calibrated camera view, or it may be a projective transformation, okay. with respect to the uncalibrated camera views, right? So this projective, we can say, if it is related by a projective transformation, we call it as a projective reconstruction, right? And if it is related by, let's say, a similarity or transformation, then we call it as a similarity reconstruction. If it is related by an affine transformation, we call it as an affine reconstruction, okay? Now here, as I said, for the true reconstruction, we represent it this way. Okay. So what that means is, so let's say I have X cap here, right? So this X bar here represents the actual 3D, actual 3D points in the scene, right? Now, if I am applying, let's say, some camera parameters, if I'm applying P and P dash here, what happens is the image point pairs I get would be X and X dash, okay? Now, when we are speaking about projective transformation, what we are trying to say is that in this X bar that I have, right? If I'm applying a projective transformation, let's say I'm just representing it by HP, okay? If I'm applying a projective transformation, let's say I'm getting X dash, okay, which is my reconstructed scene. This is the actual reconstructed scene. This is my reconstructed scene when I tried to reconstruct using some method, right? Now this reconstructed scene and this actual scene would differ, or it would be related with each other by a projective transformation, right? And this X dash, if I try to apply the here to the camera parameters, if I apply the same transformation, so when I'm applying that, it would become PHP inverse. Okay, so if I'm applying a projective transformation to the camera parameters also, what happens is I will get back the same image point pairs, right? So I get the same image point pairs for both of these reconstructed scenes, okay, and these reconstructed scenes would be related by projective transformation. So same applies for the similarity transformation, and that would be the case of the calibrated case, right? So if the kind of reconstruction which you have done is a similarity reconstruction, then this matrix, instead of a projective transformation matrix, you can replace it by a similarity transformation matrix. Okay, now when we say metric reconstruction, okay, basically it means the same as a similarity reconstruction, and sometimes it is also called as a Euclidean reconstruction. Okay, so just remember that when you're saying metric reconstruction, basically that means that you are, or it is related, the other transformations which are allowed are the rotation, translation, as well as scaling, right? So that is a metric reconstruction. We'll be coming across metric reconstruction later on. Okay, so here, now what we were discussing earlier was that when we are trying to reconstruct using uncalibrated cameras, right? The type of reconstruction that we get is projective reconstruction, right? Or the kind of transformation which exists between the actual scene and the reconstructed scene would be a projective transformation, right? So here the projective reconstruction theorem, it states that if a set of point correspondences in two views, okay, so basically the point correspondences, let's call it as X and X dash, if they determine the fundamental matrix uniquely, that is capital F, then the scene and cameras may be reconstructed from these correspondences alone. And any two such reconstructions from these correspondences are projectively equivalent. So projectively equivalent means that they are related or they are mapped to each other using a projective transformation. So what this means, or what the theorem states, is that if you are considering two image point pairs, X, X dash, okay, from which we have also determined the fundamental matrix. Now from this we can reconstruct. So from this, let's say I'm reconstructing a scene, right? My reconstructed scene is X dash, right? And I can also reconstruct another scene. Let me call it or I can, let's say I'm calling it x1 dash and x2 dash, right? So if from the same set of image point pairs, if I'm reconstructing a scene x1 dash and another scene x2 dash, it's basically the same scene, but it is using two types of reconstruction. I have obtained x1 dash and x2 dash. In that case, these two will be related. These two reconstruction scenes would be related by a projective transformation. Okay, so that is what the projective reconstruction theorem states, right? Or another way of stating it is this way, that is, suppose that xi and xi dash is a set of correspondences between points in two images, and the fundamental matrix F is uniquely determined from the condition xi dash transpose fx is equal to 0 for all I. Okay, so it is the same as what I said in the previous slide. Okay, it's just a formal statement, that's all. So let's say I have the image point pairs x and xi dash, okay, and from that I compute the fundamental matrix using this condition x dash fx is equal to 0. Then let p1 dash x1, okay, let these be the camera matrices and the reconstructed points of one particular reconstruction, and let's say p2 dash x2I are the reconstruction, another reconstruction but obtained from the same set of image point pairs, right? Then what I can say is that this set of reconstructed scene or parameters and this set of reconstructed parameters, they are related to each other. They're mapped with each other using a projective transformation. That means I can say that there exists a projective transformation matrix H, okay, such that I can write P2 is equal to P1 H inverse. That is, if I apply the projective transformation to P1, I will get P. Okay. Similarly, if I apply projective transformation to P1 dash, I get P2 dash. And if I apply projective transformation to x1I, then I get x2I. Okay. So like that, if I apply the projective transformation matrix to all the points in this particular reconstructed scene, if I'm able to get back, or I will be able to get back this particular scene, right? So then what I can say is that then I can say that this two reconstructed scenes are basically in the projective space, okay, because they are related by the projective transformation, right? So both are lying in the, or both are represented in the projective space. Okay, so it implies that one may compute projective transformation of a scene from two views based on image correspondences alone, right? And just using image correspondences and without knowing any of the camera calibration parameters, you would be able to reconstruct image scenes, right? And those image scenes which you are able to reconstruct are related with each other using a projective transformation. What that means is, let's say I have applied a method and obtained a reconstructed scene, then that reconstructed scene would be or it can be mapped to the true reconstruction scene using a projective transformation. Okay, so over here what I can say is, okay, let's say I have two images or image views of this particular house. Now this house, this location, what you see here is my 3D scene, okay, and these are two views of the same 3D scene, right? Now from this two views, what I'm trying to do is I can reconstruct the image, right? Now when I'm trying to reconstruct that 3D scene in the projective space, this is how it's going to look like. So this is one reconstructed view and this is another reconstructed view, right? So in these two, what I can say is, now these two are obtained from these two images itself, right? But here, if I'm observing in the projective space, as we have already discussed earlier, the lengths of the different lines are not preserved, right? The angle between the different lines are not preserved. So if you just compare the actual scene over here, you see that the lengths as well as, so these two lines, if you see, these two are parallel to each other, these two are having the same length, these two also are parallel to each other and having the same length, and you have a particular angle between the two lines. Now the same angle exists, okay, between the different, so if you're looking at these once these would be 90°, okay? But those angles between different lines as well as the parallelism of the lines are not preserved when you're dealing with the projective reconstruction, right? But the only thing which is preserved in the projective reconstruction is the straightness of the lines as well as the fact that two lines intersect. That means here in this scene, I know that this line and this line intersect, right? So similarly, if I look at this reconstructed view, what I see is that yes, these two lines are intersecting here also, right? And in this reconstructed view, again, what you see is that these are also intersecting. So the intersection of the lines as well as the straightness of the lines would be preserved when you're doing a reconstruction in the projective space, okay? But other than that, the length, the angles, etc., all these are not preserved in the projective reconstruction, okay? So this is something we've already discussed in the first few classes, right? Okay, so let us say the true Euclidean reconstruction. That means the true reconstruction which we have just using another notation. Let us say it is represented by PE, P dash E and XE. That means P and P dash are basically the camera parameters and capital X is the actual points. Okay, and you're saying that these are the true reconstruction in the sense these are the true image, 3D points in the scene, right? And the projective reconstruction, let us say it is given by P, P dash and Xi, right? Then what I can say is these two are can be mapped with each other using the projective transformation matrix H such that I can write capital PE is equal to PH inverse, capital P dash E is equal to P dash H inverse, and capital XEI is equal to HXI. Okay, and here H basically represents the projective transformation. So projective transformation means it can be any 4x4 homography matrix, okay, because it is now in the 3D space, right? Okay, now when we are so what we saw here is regarding the projective reconstruction or projective transformation. Okay, now as I said earlier, in projective transformation, all that we need to, or we can find out if two lines intersect or not. So if any two lines intersect, okay, and if they are intersecting, or the two lines which are intersecting in the actual scene is also intersecting in the reconstructed image, then we can say that the reconstruction is in the projective space, okay? But apart from that, you do not have any other constraints when it comes to projective reconstruction, right? And in projective reconstruction, all that you need is image point pairs. So you have x dash, okay, you need to determine x dash, and from this x dash, whatever scene you are reconstructing would be in the projective space, right? So the only steps that is involved is you have x dash. From there you compute capital F, which is the fundamental matrix, and from that you can calculate the camera parameters P, P dash, and then using triangulation you can calculate capital X, which is the reconstructed 3D point. Okay, so the projective reconstruction involves only these basic steps, and what we see is that it is a very simple process, like finding the projective reconstruction, right? Now, after finding the projective reconstruction, or finding or determining the reconstruction in the projective space, if we want to transform that or convert that to a fine reconstruction or a similarity reconstruction, we will need some extra information. As I said earlier, when it comes to reconstruction ambiguity, right, there needs to be some extra information in order to determine or in order to transform from the projective space to the affine space, okay, or to convert from the projective space to the Euclidean space. So what are those extra information that is required, that we'll see later. But what you have to remember now is that first, only after you do a projective reconstruction of a scene, that would be the first step in order to find out a affine or a metric reconstruction. Okay, so as you know, here when you are calculating for this, if you want to find out what is the measurement of the these lengths, or if you want to measure the angles, etc., measurements would not be possible in the projective space. For that, you have to convert that into a Euclidean space, right? So for converting to a Euclidean space or a metric reconstruction, okay, you will have to first find the projective transformation or reconstruction, and from the projective reconstruction you have to, only then you can find the metric reconstruction by adding in a few more information to ensure that the lines, the parallel lines are ensured to be parallel in the reconstructed image, and the lengths are preserved, etc. So to ensure the parallelism or the lengths to be preserved, you add in certain information later, but the first step is always projective transformation, and that projective reconstruction we can do using these three basic steps. Okay, so now how do you find out, or how do you exactly determine the metric reconstruction from the projective reconstruction, right? So what I said earlier was that first you need to find a projective reconstruction, and from the projective reconstruction, then you can convert it into a affine reconstruction or Euclidean reconstruction based on the application or your requirement, right? So there are two ways by which you can approach that. One way is using the stratified approach. Stratified approach means first you convert from the projective transformation, you convert that to affine transformation, and then from the affine you convert it into the metric or the Euclidean transformation. Okay, so this step-by-step approach where you first convert to affine and then to metric reconstruction is what you call as the stratified reconstruction. Now, apart from that, there is also a second method, which is direct reconstruction. That means from the projective reconstruction, you can directly, calculate the metric reconstruction. Okay, so there are two methods of reconstruction. First is the stratified, which we will be discussing today. Second one is a direct reconstruction, which we'll be seeing in the next class. Okay, so let's first look at how the stratified reconstruction works. That means now that we have the projective transformation, as I said earlier, how we find the projective reconstruction is given the image point pairs, if we calculate the fundamental metrics, and from there if we calculate the camera parameters as well as the reconstructed image point using the epipolar geometry or the triangulation method, what we get, the image that we get would be in the projective space. And why we say that it would be in the projective space is because the straightness of the lines would be preserved, as well as the intersection between the lines would be preserved, right? Now, from the projective space, if we have to convert to the affine space, we know that in the affine space, the parallelism of the lines are preserved, or it needs to be preserved, right? So what we do is we need some extra information in order to ensure that it is, from the projective space, it is converted to the affine space. So if you can recall earlier, we have seen how we can exactly go from the projective space to the affine space. Okay, so what we saw is that, now let's say if we are dealing with 2D space. Okay, in the 2D space, what we've seen is, let's say in the projective space, okay, if we can identify a line at infinity, so let's say you have a line at infinity, if we can identify this line at infinity, then what I can say is you are no longer in the projective space, but you are in the affine space, because now you have a line at infinity, and basically that means that the parallelism is preserved. And given this line at infinity, along this line, if we are able to identify circular points, that is points at infinity, okay, if we are I'll just write it as circular points here. These are concepts which we have already seen in the first few classes, right? So if you are able to identify the circular points along this line at infinity, what I can say is that we are no longer in the affine space, but we have moved on to the metric space or the Euclidean space. I'll just call it as metric space over here. Okay, it basically means the Euclidean space, right? So this is in the case of 2D. So if you're dealing with a 3D objects or in the 3D space, Given the projective transformation, instead of finding the line at infinity, what we do is we find a plane at infinity, right? And that plane, let me represent it by pi infinity. So if we can identify that there exists a plane at infinity, okay, then you can say that you are in the affine space and no longer in the projective space, because here when we have a plane at infinity, the parallelism is preserved, right? Now, from the plane at infinity, if we can identify the conic, okay, so absolute conic, okay, absolute conic is, it is analogous to finding the circular points on the 2D space. In the 3D space, it becomes absolute conic. And if we are able to identify this absolute conic, then what I can say is I'm no longer in the affine space, but I'm in the metric space. Okay, so just here I can represent it this way. Instead of a line, what I have is basically pi infinity. So this is my plane at infinity, let's say, and the absolute conic, let's say I'm representing this way. Okay, now what I'm doing here would be, instead of finding the absolute conic directly, okay, we would be finding the image of the absolute conic and then projecting it. Okay, so we'll discuss that later on. So for now, what you need to remember is the extra information that we are adding, okay, to move from the projective space to the affine space would be first to identify the plane at infinity. So then you are in the affine space, and from the affine space, if we can find the absolute conic, then I can say I'm in the metric space or the Euclidean space, right? Now, in order to find this pi infinity, okay, pi infinity means basically the plane at infinity. Okay, you need to have some extra information with regard to that, right? So here, let's say we have determined the projective reconstruction, and we obtained the points p, p dash, and xi is basically the projective reconstruction that we have obtained, right? Now what we need to do is we need to find this plane at infinity, which is pi infinity, okay, in order to say that okay, I'm no longer in the projective space, but I am in the affine space, right? Now, as I said earlier, we need to use some extra information in order to find this pi infinity, right? And one method that we can use is the seeing constraints, okay, which we'll see later how exactly we can identify the seeing constraints. But let's say that using some extra information, we have already found out pi infinity. So this is basically pi infinity, right, which we have computed and which we have found, right? Now, given this pi infinity, what I need to do is the actual coordinates of pi infinity, that is plane at infinity, will have the values 0, 0, 0, 1, right? So what I need to do is I need to find what is the transformation, okay, between this pi infinity as well as this. That means if I can find a plane, okay, which can be mapped to the plane at infinity, which is given by 0, 0, 1, then I can say that I am in the affine space. I'll just repeat once again. Here, let's say I have identified a plane pi, okay, which can be mapped to the plane at infinity, which is given by the coordinates 0, 0, 0, 1. Then what I can say is I'm in the affine space, right? So using this information, so what that means is now I need to identify this particular h, okay, which is able to map this pi infinity to, let's say, this I'll just write it as pi infinity bar, okay, which represents that this is the true plane at infinity, right? So if I'm able to find out this particular transformation matrix, right, which can map this pi infinity to pi bar infinity, then by applying this h to all the points in the image, right, then I can convert that to affine. So given the image in the projective space, if I can identify this h, okay, then what happens is I can convert it into an affine reconstruction. Okay, so basically what I'm doing is I'm trying to find the image or the projective whatever image I have obtained in the projective space, I'm trying to convert that into a affine space. Okay, so and thereby obtain an affine reconstruction, right? So in order to obtain that affine reconstruction, I need some kind of a mapping function here or some kind of a transformation matrix over here in order to map from P to A, right? Now in order to find this H, the information that I'm using is I'm trying to find out the plane at infinity, which is given by pi infinity, and trying to map it to the true coordinates 0, 0, 0, 1, right? So on mapping that, whatever is the transformation matrix that I'm getting, H, okay, that would give me the mapping between this projective space and the affine space for the particular image that I'm considering. Okay. So now here what we need to know is how to find this pi infinity, right? Because only if we know pi infinity can we try to map it together to find H and then apply this to get the affine transformation. So how do we find this pi infinity? In order to find this pi infinity, I need to use some information, right? So what I'm doing is I'll be using some information with regard to parallel lines. Okay, so just discussing the point once again, we want to find out H, right? Such that H inverse transpose pi is equal to 0, 0, 0, 1, right? That means mapping this pi to the pi infinity with respect to the transformation matrix H, right? And this transformation matrix H is given by I0, which is the identity matrix, right? And then you have the pi transpose, where this pi is basically the plane at infinity that we are trying to find, right? So once we know this H, we can easily reconstruct the image in a fine space. But in order to find this H, what we need to know is we need to compute this pi, right? Now, how do you find out this pi is what we're seeing next, right? So in order to find out pi, there are different methods that you can use. And one method which can be used is, or one method which we are going to discuss here, a simple method is using scene constraints, that is parallel lines. Okay, that means we know that parallel lines would, are preserved in affine space, right? So using that information, using the information on the parallel lines which are present in the 3D scene, what we are doing is we are trying to find out what is the point at infinity at which these lines intersect. Okay, I'll just explain with respect to this particular image. That is, I have three different images, okay, of the scene. Okay, so I'm taking the same scene, which is the house, right? Now I know that these lines, right, which are present here, they are parallel to each other, and I know these lines are parallel to each other, and I know, okay, I have identified these particular lines which are also parallel to each other. So if I can identify different set of lines which are parallel to each other, I can just project it to find out a point at infinity, right? For these for this set of parallel lines, let's say the point at infinity which I have identified as L infinity 1 for this set of parallel lines, and let's say if I take another set of parallel lines, it is represented by L infinity 2, and let's say for another set of parallel lines, I am identifying another L infinity 3. Okay, so once I have different points at infinity with respect to these different set of parallel lines, I can make use of all these three information, that is L1 infinity, L2 infinity and L3 infinity together in order to find out what is the final plane at infinity. Okay, so given these points at infinity, okay, I can find out, and these 3 points, because it comes from different set of parallel lines, I know that it's not the same points at infinity, right? So using these 3 points, I can find out, that is using at least 3 known collinear points, I can find out what is pi infinity, that is a plane at infinity. Okay, so this method is what you call as the scene constraints using the parallel lines. Okay, so it is not just this, you can use several other information, but this is just one example of how you can make use of extra information in order to find out the pi infinity or the plane at infinity. Okay, So after using this information of the parallel lines from the different images and finding out pi infinity, what I can do is, now given pi infinity, now you can try to map this pi infinity to 0, 0, 0, 1 coordinate, right? So this mapping would be with respect to h, right? And this h, after determining this h can be applied to all the image points which are present in the projective space, and that will give me what? The affine space or the affine transformation that I'm looking for. Okay, so that completes that whole method of how you can convert from projective to affine transformation, right? Now, similarly, what I can do is, in the stratified method, as I said earlier, we convert after converting from projective to affine, you have to convert from affine to metric, right? So we'll see how to convert that. So before that, another example of how we can make use of the parallel lines concept. So let's say I have two images again, two different images of the same scene, but since you have this particular design here, I know that okay, these are parallel lines here, these are parallel lines here, and so on, right? So I know these are parallel lines, so on projecting these parallel lines I would get a particular point. Let's say I represent that by L1 infinity, okay, and here another set of parallel lines could give me another point L2 at infinity, right? And then joining these two together would give me L infinity, which is basically my line at infinity. Okay, so just giving that concept of vanishing line. So this is what you call as vanishing line, and these points at infinity is what you call as vanishing points. Okay, so just some terminologies that you need to remember, and this is just another representation of the same concept where you are trying to identify the plane at infinity, and then from the plane at infinity you can apply that transformation in order to obtain the affine reconstruction. Now, once you get the affine reconstruction, next step in the stratified approach would be to convert that to a metric reconstruction, right? So affine means it will preserve parallelism. Metric means it should preserve the length as well as the angles which are present in the image, right? And that is important when you have to make some geometric measurements from the images, right? So if you have to go from affine to metric reconstruction, again, as I said earlier, we need to have some kind of extra information, right? So after identifying the plane at infinity, okay, you need some information regarding the conic, okay, the absolute conic, in order to convert that from the affine space to the metric reconstruction, right? So what the information that we make use over here is determining the absolute conic, right? And absolute conic, it is analogous to the circular points which are present in 2D space, right? The circular points which are present which are lying on the line at infinity in 2D space. Absolute conic would refer to the conic which is present on the plane at infinity when it comes to 3D space, right? So here what we do is as I just mentioned earlier, that is, let's say this particular, this is my pi infinity, which is the plane at infinity, okay, and let's say I have and absolute conic here, right? Now what I'm trying to do is, instead of computing the actual absolute conic which is present in pi infinity, that is in the 3D space, what I do is, instead I just try to compute an image. So what I do is, I take an image and I try to compute the image of the absolute conic, okay? And once I convert, or once I compute what is the image of the absolute conic, I simply try to back project that into this pi infinity, right? And try to find out what is the computation with respect to 3D space. So that is the approach that I'll be following, right? So in order to find out what is the image of the absolute conic, again you will need some information there, right? So we'll just see that. So here, image of the absolute conic means it is a conic in the in the particular image that I'm considering, and then what I do is I just try to back project this in order to obtain the actual absolute conic at the plane at infinity, right? So in order to do that, what I do is, so again, as I said earlier, what we are trying to do is we are trying to convert from the affine space to the metric space, right? And for converting from the affine to the metric, again, we will need a transformation matrix, right? So here, suppose that in the affine reconstruction, we have obtained the image of the absolute conic. So image of the absolute conic, it is abbreviated as IAC. Okay, IAC, image of absolute conic. So let's say the image of absolute conic. Okay, it is given by omega. You're using the denotation omega, right? And let's say the camera matrix is given by P is equal to capital M small m here, okay, where here capital M is a matrix and this M is a vector, a column vector, right? So in that case, I can say the transformation matrix, okay, is given by A inverse 1, where A is given by A transpose is equal to M transpose omega M the whole inverse. So here what you need to remember is the transformation matrix that I'm looking for. That means what I'm trying to do is I'm trying to convert from the affine space to the metric space or the Euclidean space. And for that, I need a transformation H, right? So this transformation H can be obtained only if I know omega. That means here this H is a function of an element A, which is dependent on the absolute conic value, okay, which is given by A transpose is equal to M omega M. So that means A is a function of both the absolute conic parameters as well as the camera parameters, and together with the camera parameters as well as the absolute conic parameters, okay, I can find out what is H. And once I know H, I can convert from the affine to the metric space, right? And on converting from the affine to the metric space, so that completes the stratified approach where we are converting from the projective to affine and then from the affine to metric. So now, how do we calculate the image of the absolute conic? So what I've said earlier is that you need to know this parameter omega, because from this omega and along with the camera parameters m, you will be able to find out h. And once you know h, you can convert from the affine to metric, right? So in order to do all that, now you need to know what is the, or how to compute the image of the absolute conic. Now in order to compute the image of the absolute conic, you need some extra information, which is which could be, you can use different kinds of information, prior information for this, okay? So one example of using a prior information is using the known internal parameters of the camera. Okay, so that means, let's say I have a point on pi infinity, which is the plane at infinity. In that, let me consider I have a point which is given by capital X infinity d transpose 0. Okay, so here the general camera is given by capital P. Okay, where I can represent it this way, that is, I have it as K R. K is the internal parameter that I'm having. R is basically the rotation parameter, okay? And here I have decomposed it as I and C. C is inclusive of the translation parameter, the scaling parameter, and so on, okay? Into D and 0, where D is basically my X infinity, or the point at infinity, okay? So I can, the actual, formula that you have, x is equal to px, okay? In the case of point at infinity, I can write it as small x is equal to capital P x infinity, right? Now this capital P, I can decompose that into the internal parameters and the external parameters. So the whole of this becomes the external parameters, right? K alone is the internal parameter. right? Into I'm multiplying that with the x infinity or the point at infinity, right? So on computing, what I get would be equal to kr day. That means it is equivalent to multiplying the point at infinity with the internal parameter of the camera as well as the rotation matrix that you have here, right? So on computing this further, what we see is that the what is it, the transformation matrix that you have, right, H, it is given by K into R. Or I can write it this way: the image of the absolute conic omega can be written as K transpose the whole inverse. Okay, that means if I once I find out H, right, once I find out what is the transformation matrix from the previous slide, right, I can just use that in the information of or in the equation which relates H and omega, and from there I can find out what or I can obtain omega is equal to K transpose the whole inverse. So here the bottom line is, if we are using the internal parameters of the camera as the external or extra information used to derive the absolute conic image of the absolute conic or IAC measurements, I can write omega is equal to K transpose the whole inverse. So where K is the internal parameters. Okay, so if the internal parameters of the camera is known, I can just use this information or this equation to find out omega, right? And once I know omega, I can use that to find out the transformation matrix H. And once I know H, I can use this to transform from the affine space to the metric space. Okay, so this is how we do the stratified approach. I'll just quickly explain that once again. In the stratified approach, you have two steps. One where you convert from the projective space to the affine space, and then the second step is where you convert from the affine space to the metric space. So in order to go from the projective space to the affine space, what you need to do is you need to find out pi infinity or the plane at infinity, right? And in order to find out the plane at infinity, what I do is I identify what are the parallel lines, different set of parallel lines which are present in the two images, and try to project that to get different points at infinity. And these different points at infinity together gives me the information regarding pi infinity. And once I know pi infinity, I can map it to the true plane at infinity, which is given by the coordinate 0 0 0 1. By mapping this to this, right, that mapping transformation H will give me what is the transformation matrix which is required to convert the image from the projective space to affine space. That means I need to apply this H to all the points in the projective reconstructed image in order to get the affine reconstructed image. Now from the affine reconstruction, in order to find the metric reconstruction, the information that I make use of is the absolute conic. That means I try to compute the image of the absolute conic with respect to the internal camera parameters. And once we know the omega, which is the image of the absolute conic, I can use that in the previous equation to find out what is H, right? And once we know H, that is the transformation matrix, I can apply that to all the points which are present in the affine reconstructed image in order to get the metric reconstructed image. Okay, so that is the stratified approach. That is one approach by which you can convert from the projective space to the metric space for a reconstructed image. Now there is a second method too. Second method is the direct method, where we do not we do not convert to the affine. Instead, we directly from the projective space we directly convert to the metric space, and that particular method we'll see in the next class. Okay, so here this image, this gives a representation of how the metric reconstruction looks like. So if you remember in the previous case, we saw that in the projective space, the parallelism of the lines were not preserved, the angles, lengths, etc. were not preserved. So on applying constraints of constraints with respect to length and angles, right? So we're not directly doing that. What we're doing is, if when we are converting that to the affine space with the concept of plane at infinity, that is ensuring the parallelism, and then by applying the information of the absolute conic, what we'll be able to do is we'll be able to reconstruct the whole thing into a metric reconstruction. And from the previous two images, the metric reconstruction becomes like this, right? So after metric reconstruction, the image would look like this, where you see that parallel lines would be preserved as well as the angles would be preserved. Okay, so these are just two views, but here this is the reconstruction, final reconstructed image along with the texture information. Okay, so next is the direct reconstruction, which we'll see in the next class. Okay, so does anyone have any doubts so far? In today's class, what we discussed was what are the three basic steps to go about with reconstruction for an uncalibrated image or uncalibrated camera. Then we discussed on how or what are the different reconstruction ambiguities. That is, with respect to position, there could be a Euclidean or you can say that there is a Euclidean transformation between the actual scene and the reconstructed scene. And if you are also considering the ambiguity with respect to scale, you can say that there is a similarity transformation between the reconstructed image and the actual image, right? Then after discussing about the different ambiguities in the reconstruction, we saw how we can reconstruct an image, or what we saw was that, yeah, how we can reconstruct it, an image in or a scene in the projective space. So the three steps would be, once you know the image correspondences, you can just calculate the fundamental metrics and then go about with finding the camera parameters as well as finding the reconstructed 3D point. And this 3D reconstructed point would be or it can be mapped to the actual scene, okay, by using a projective transformation. Now, if we want to convert that into a metric transformation, so we might have to convert it into a metric space if we are doing some geometric measurements from the image scene. Like for example, let's say calculating the length of the pillars or calculating some distance between different objects or so on. So if we have to transform that from the projective reconstruction space to the metric reconstruction space, you can either follow a stratified approach where you convert first to affine and then to metric, or you can use a direct approach where you directly convert to metric. So if you're using the stratified approach, first you convert to the affine space by determining what is the plane at infinity, and we find out the plane at infinity by identifying the parallel lines and then finding out the points at infinity where the parallel lines meet, and then from these points at infinity we find out the plane at infinity or pi infinity, right? And then we try to map that to 0, 0, 0, 1, which is the true plane at infinity, in order to find out what is the transformation matrix H, which is basically the transformation matrix that maps between the projective space and the affine space for that particular reconstructed scene. Okay, and similarly then we try to map from the affine space to the metric space by finding out or by computing the image of the absolute conic. And for that we make use, or what we do is we first compute the image of the absolute conic and then try to back project that in order to or back project that to the plane at infinity, and from there we obtain the metric reconstruction. And this is an example of how the images would look like. And the second method is a direct reconstruction, where we directly reconstruct the metric space from the projective space, and that will continue in the next class. Okay. Is there any doubt for any of you? Okay, if there are no doubts, I'll just launch the quiz now. Okay, I'll be posting the quiz at 5:20, and if please ensure that you submit it within 5 minutes itself. Uh, Try to submit it within 2 or 3 minutes so that you can submit it on time. I'll be closing the assignment or the quiz. There are only 2 questions, so I'll be closing that within 5 minutes.